Well, the first technique we're going to look at is partial fractions. So, how to handle it. So basically when we're going to find the integral and we're dealing with a fraction which has a polynomial on top and the polynomial on the bottom. So how do we handle this sort of fraction? So the first thing we need to look at is what are the degree of the two polynomials. And if the degree of the numerator is bigger than or the same as the degree of the denominator, the first thing you do is a polynomial division to simplify it out a bit. Then once you've done that division, you'll get a fraction where the degree of the numerator is less than the degree of the denominator, plus some polynomial. Well, the polynomial part is going to be easy to integrate because that's just add 1 to the power over the power. How do we deal with the fraction that we're left with? Well, as we always do with fractions, algebraic fractions, factorise it. That's going to make life a lot easier. Now, when you factorise a polynomial, as we now know, we should end up with a combination of linear functions and quadratic functions. We can always factorise down to that. So if we have a linear factor in there, then one of the fractions I'm going to have is a over x minus a. It's sort of like going backwards in the algebraic fraction question. We're sort of saying, hey, here's the answer. What was the question we originally had? What were the fractions adding together to get this? So we must have had a fraction where each of those factors are in the denominator. So we'd have a fraction for x minus a. And I just put a constant on the top. Now, if it's x minus a to the power of something, then the way I tend to do it is I'll write down one fraction for every power. So however many that needs to be. That leaves me with a quadratic, and if I have a quadratic, then on the top I put a linear function. And that's pretty much it. Okay, so that's the idea. How do we deal with it? So x squared on x plus 1, well, I've got a quadratic on a linear function. Do a polynomial division. If you don't see it straight away, we can go back to long division. X plus 1 to x into x squared. Let's see, that goes x. Minus x. No, x will still go into minus x. Minus 1. A remainder of 1. Okay. So I can rewrite that fraction as a polynomial, x minus 1, plus a fraction. Excuse me. Now in this case, the fraction's easy enough to integrate. Hopefully you recognise it. And we've got a log function there. So I know that's going to be half x squared minus x plus the log of x plus 1. Okay. So 3 on x squared minus x. Don't need to do a polynomial division here. But let's factorise the denominator so we can see what we've got. And I've got 2 linear factors. So I've got x on x minus 1. So what I know is I must have originally had these 2 fractions adding together, and I end up with an answer of 3 on x minus 1. Now if I can work out those 2 fractions, integrating becomes easy, because again I'll just have log functions. So I just need to work out what a and b are. Well, if I multiply both sides by x minus 1, I can create a nice little identity to solve. Now, yes, I could expand this out and equate coefficients. That's one way of doing it. Or, clever use of substitution, picking some obvious numbers will find it as well. So, I chose x equals 0 because that's going to make the b disappear altogether, and I just end up with, negative a is 3. So I know a is negative 3. Now, to work out the b, I'll make x equal to 1. That'll now make the a disappear. And so I just get b equals 3. Okay. So I've ended up with 2 fractions, both going to be log functions. So I've got minus 3 log x plus 3 log x. I tend to, if the coefficient is the same, I'll pull it into 1 log. So negatives go on the bottom, of course, because we know when it's minus log, you divide. So I end up with 3 log x minus 1 on x. If the coefficients are different, as far as the number, I'll usually just leave them. I mean, you could always still make them the same by bringing that number in as a power. You can still combine it into 1 log, but I don't know, it's just the habit I've got into when I'm doing these. All right, let's have a look at this one. X plus 5 on x squared minus 3x minus 10. Well, the bottom factorises, so again I'll create 2 linear denominators. This time the answer is going to be x plus 5 over x minus 5, x plus 2. So multiply by the denominator. Okay. Clever use of substitution. I'll pick, which one did I do first, I wonder? Because the two numbers I'm going to sub in are going to, of course, be, minus 2 and 5 are going to be the ones that work here. So if I do minus 2, I end up with b as minus 3/7. If I do 5, I get a as 10/7. So let's create it. I mean, you could always pull the 1/7 out the front if you wanted to, I suppose. That'll make life a little bit easier. But again, we've now ended up with two things that are going to become log functions. So I have 10/7 the log of x minus 5 minus 3/7 the log of x plus 2. That's what I'm here. I'm not going to bother mucking about bringing that into one log. I mean, I could pull the 10 in and make that x minus 5 to the power of 10. I'd have 1/7 out the front. I could pull the 3 in, make it x plus 2 cubed. Again, I'd have 1/7 out the front. Then I could combine the two logs. But I guess it all depends what I'm going to end up doing with that answer, whether that's useful or not. X cubed plus x. Well, when I factorise this one, you'll notice I get a quadratic factor, x squared plus 1. Doesn't factorise. So this time when I set up, the linear, I've got a over x, but for the quadratic denominator, I'll put a bx plus c on top. So it has some linear function on the top. Again, multiply by the denominator. All right, there's going to be some easy substitutions here, and some not so easy substitutions. Which one would you do first?
X equals 0.
X equals 0 will make both the b and the c disappear. So that gets me a equals 1. Now, there is a substitution that will make the a disappear. And the hint is, if you were doing extension 1, you wouldn't think of it. Yes. If you substituted I into this, then a will disappear. So if you've got x equals I, and then we get minus b plus ci equals 1, and now I just equate the real and the imaginary part, and I get b and c. So b is equal to -1, c is equal to 0. I end up with 1 on x, that's a log function. The second one again is a log function. So you get x on x squared plus 1. So we have got log of x minus a half of log of x squared plus 1. Let's do this example where I've got one of the ones where I've got a repeated root here and also a quadratic as well. So I'll set this one up. I'll have a over x plus 1, b over x plus 1 squared. Now, as I say, I do it that way. Some people will say, no, I've just got a quadratic factor, x plus 1 squared, so on the top I'll put ax plus b. And if you think about it, it's exactly the same, because if I was to combine these two things into one fraction, I'd end up with that linear one. But I just think it's easier to do it this way. Now, and of course I've got the linear function cx plus d. Okay, let's pick some numbers here that's going to make things disappear. What's the first one you want to do?
-1.
Yeah, I think -1 is going to be the easiest first of all. -1 will make the a, the c and the d disappear. So b is -1/2. Then we could do I. Now when you do I, you end up with, and be careful with that one, because there's a little bit of calculation to do with the cx plus d and so on, but you end up with minus 2c plus 2di equals I, equating real and imaginary. I still haven't got what a is. Now, I'm just going to pick something that's easy to substitute, because I know what b, c and d are. So I'll just pick x equals 0. I end up with 2a plus b plus d. I know what b and d are. Okay, actually turns out a is 0 after all that. Okay, my integral. So I end up with minus a half on x plus 1 squared, plus 1 on 2x squared plus 1. We haven't got a log function at last. The first one there is just add 1 to the power over the power. Remember, du on u squared will be... first day back. Du on u squared becomes? Minus 1 on u, yeah. But in this case, instead of u, I've got x plus 1. Denominator x squared plus 1, we've got inverse tan. So, I've pulled the half out there, you'll notice. To make the first fraction a little bit more obvious, I've put it in index form. But, there we go, verse 10. But that's what I was saying before we broke about the non-standard integrals. You know, that sort of idea of du on u squared, it comes up a lot. So rather than doing substitution and rather than putting it into index form all the time, we just remember, well, du on u squared, that's minus 1 on u. Then you go straight to the answer. And there it is, minus 1 on u, in this case, x plus 1. Okay. There is an alternative method you may have heard of. It's called the cover-up idea. Yeah? So it works nicely when all the factors are linear. This is where it works really quick. So what do? To find a, you substitute a into our fraction on the right-hand side, but forget about the x minus a, because of course you can't have 0 on the bottom of a fraction. But you substitute it into everything else. So you end up with function a on a minus b, a minus c, and so on. Then to find b, I'll substitute b into everything, just not the x minus b, because that would create 0 on the bottom of the fraction, and that makes life difficult. So I'll get function b on b minus a, b minus c, and so on. And I just do that for all of the pronumerals that I need to do it for. So to find c, I'll substitute c into the right-hand side, except for the x minus c, because that would create 0, and you can't have 0 on the bottom of the fraction, and that will get our answer. And so on and so on. So let's go back to some of the ones we had. So if I was to look at this one now and go, well, a over x plus b on x minus 1, if I want to work out a, I'm going to substitute in 0 to the right-hand side, except I'm not going to put it into x because that'll give me 0. So I end up with negative 3. If I want to work out b, I'll substitute 1 into the right-hand side. I just won't use the x minus 1 because that'll create a problem. And there we go, b's 3. The reason it's called the cover-up method, because what some people do to make sure they don't substitute it in, is they get their hand and I'll just cover up the x. Okay, that's what I'm substituting into. Oh, I'll just cover up the x minus 1. Oh, that's what I'm substituting into.
So why does it work?
The reason it works is because that problem Michael talked about before is, how can this be an answer? Because you can't have 0 on the bottom of the fraction. So there we get our two constants. All right. So if we have this one, if I want to work out a, I'll substitute in 5, I get 10 on 7. That was our answer. If I want to work out b, substitute in negative 2, I get negative 3 on 7. Bang, got the answers. Okay. So that's called the cover-up method. Works beautifully, as I say, when you've got linear factors. And you'll see some textbooks, I think Terry Lees goes through this, but they only ever explain it for linear factors. So when I saw it, I went, oh yeah, it's a nice idea, but surely that idea can be transferred through. And it can. If we think of complex numbers, then you can still use the same idea. Right? So here was our a on x, bx plus c, x squared plus 1. Well, to work out the a, easy enough, I'll make x equals 0. And I'll get 1 over 1, so a is 1. Now, to work out the b and the c, I've got x squared plus 1. Well, what's going to make x squared plus 1 equal to 0? X plus I. What you substitute in I, and we get bi plus c, 1 on I, realise the denominator, equate the real and the imaginary, bang, c is 0, b is negative 1. So you can still use the same idea. So what would I have done with this one? Well, working out a, easy enough. Substitute in 1, we get 1. The right-hand side, well, what's going to make 4x squared plus 1 equal to 0? So if you substitute in I over 2, this is where you start questioning and you go, oh, is this technique the best way of doing it? Because there's a bit more calculation. You might think, oh no, it's probably just easier to do it the other way. I mean, that's just where you've got to make a decision. But it does work, because eventually, when you tidy it all up, that right-hand side does become 1 minus 3 on 2i. So b is minus 3, c is 1. So the idea works. The question is whether that's the best technique for that question. What about if you got multiple factors? Bit more work with multiple factors. So you got the x minus 1 and the x minus 1 squared, because to work out b, I would have said substitute in 1. Oh, but hang on. To work out c, I'd substitute in 1. Well, which one will it work out, the b or the c? Let's do a first of all, get that out of the way. I mean, there's no dispute there. Substitute in -2, I'm going to get a. The higher power is the one that'll work for. So whatever the highest power is. So to work out c, I can substitute in x equals 1. Okay, I now have a, I now have c. I've got a problem with b. So now I'll just do a simple substitution. So I might make x equals 0, because I now know what a and c are. So if I make x equals 0, and put it into our fraction, and we get, eventually, there is, b is 2. All right, let's try this one. I've got a repeated one. I've got a quadratic as well. Would it have been a good technique for this one? Let's see. Do the easy ones. So do the b. We've got -1/2. ci plus d, it turns out okay. Ends up being 1/2. So I've got c, I've got d. Sub in 0. And I get a plus b plus d equals 0. And there we go, a is 0. So it wasn't too bad for that particular one. What happens if you get a quadratic denominator that can't be factorised? X squared plus 4x plus 5. What do I substitute in to make x squared plus 4x plus 5 equal to 0? Well, no, the idea works. Okay, I'll work out a. That's the easy bit. Now to work out what to substitute in, I'll complete the square for x to see what makes x squared plus 4x. In other words, solve x squared plus 4x plus 5 equals to 0. And it turns out to be, okay, -2 plus I would be what I'd substitute in for this one. Oh. Yeah, exactly. This is the point where you go, I'm not going to use this technique. Okay. But it will work. Let's just persevere and prove it does. So substitute in -2 plus I. Brilliant. Right-hand side, bit of manipulation. It's not too bad, actually. It's not as bad as we originally thought it was going to be. And there we go. B is -1. C is -3. All right. So in our Patel, we've got something to do there. In our Cambridge,